There we go. Can't divide by 0. We talked about that at the end of last class. We mentioned that dividing by 0 is just mathematically, it's nonsense. It doesn't make any sense at all. So what we're going to do today is we're going to use some pretty funky methods to solve some equations here. But when we start off, some of the equations that we're solving are going to have to invoke this idea, or evoke the idea that you can't divide by 0. We have to bring that into bear. So let's see how that's going to go. Let's say we wanted to solve something like this. So solve.
You muted me?
Earlier, but I think you're unmuted now.
Okay, good. I forgot to turn on the big screen, so my fault.
No worries. Okay, so say you're asked to solve something like that, and that looks quite a bit nasty. The good thing about today's class, though, is that we're going to be forced to solve some quadratic equations just as we're working. There's no way around it. There's no way to dance around that. So that'll be kind of a pseudo review for section 1.4, which was concerned with solving quadratics. So this is called a rational equation. It's rational because each, or the members of the equation are all rational expressions, meaning something divided by something, and generally speaking, your variable is in the denominator. And that usually creates a lot of problems. The most immediate problem it creates is, well, if your variable's in the denominator, there's a chance you could plug something in for x and accidentally divide by 0. For instance, if I put a 2 right here, if I put a 2 in for x right here, that's a bad arrow. That's going to cause me to have 2 minus 2 on bottom here, and then that goes to 0, and then I'm dividing by 0. Doesn't matter what's on top. If I'm dividing by 0, that's a problem. So in order to avoid the possibility of dividing by 0, we have to put up what we call restrictions on the variable. We have to say, what is x not allowed to be? What x values create problems? And the way we go about finding those is to basically take each denominator that we see, set it equal to 0, solve for x, and whatever comes out of that, those are x values we are not allowed to use. Simply so we don't divide by 0. So let's see, let's try it out. Let's see, we got to set this first denominator equal to 0. We got to set this denominator over here equal to 0, and we got to finally set this denominator equal to 0. And now we got to solve each of them for x. This first one, bada bing, bada boom. All we got to do is add 2 to both sides. And you'll get x equals 2. And notice we're not actually solving the equation at all yet. All we're doing is deciding what should not be allowed. What are the restrictions on the variable? The second denominator is already, it's done. X equals 0 is already in the books. This last one here is a quadratic. It is indeed a quadratic. But here's what I can do with it. Notice that there's no constant term, there's no c. So what I can do is I can factor an x out right off the bat. And whoops, let me delete that. I made a mistake. Boom. Booyah. And so now what we see is that we have x is one of the factors, just x by itself, and x minus 2 is a factor. And we can set each of those equal to 0. And so that creates what looks like 2 more restrictions on the variable. But we've already kind of covered those. Those have already been covered. So just by chance, it's redundant to say that, oh, x equals 0 and x equals 2 are restrictions, and so is this 0 and 2. They're the same thing. So we really, at the end of the day, only have 2 restrictions on the variable. We're going to say x cannot be 0 and x cannot be 2. Those are going to be our problem children. Almost said childs. So now we know what our restrictions are. We know what x cannot be. What we need to do, what we endeavor to do, is to now actually solve this thing. That's something we didn't technically haven't done yet. But check this out. Here's how we're going to solve it. You noticed earlier I kind of factored this thing over here, the x squared minus 2x, and the factors looked an awful lot like what I got over here. And that's exactly true. So here's what we're going to do. We're going to factor this guy out here. Factoring here is real straightforward because we just need to take an x out. So let's do that. Now here's what we're going to do. We're going to multiply both sides of the equation by the least common denominator. We're going to multiply both sides of the equation by the least common denominator. Now, let's talk about what the least common denominator is going to be. It's going to be, in this case, the x times the x minus 2. Now, again, unfortunately, when we walk into college algebra, we assume that, you've seen least common denominators before, and especially for variables. But maybe you have, maybe you're a little rusty or whatnot. What we're ultimately trying to do, our goal, is to get rid of denominators so that we can actually solve this thing. Now, when we get rid of denominators, we also have to make sure we've put our restrictions down. And that if we get anything at the end and it's one of these restrictions, we actually throw that out. So for now, let's ask for permission instead of forgiveness. Let's just multiply both sides by this denominator, x times x minus 2. So let me show you how it's going to look. That means that this guy, the 7x plus 1 over x minus 2, that means this one is going to get multiplied by this. This right here, we've multiplied it by that least common denominator. And what that's going to do is that's going to create some wonderful cancellation. And the denominators go away entirely. In fact, you could say that's the whole reason we did it. So we'll look at it piece by piece. Just saying x out here. And now there's no more denominator on that one. And all we're doing is using a math principle that says, hey, we can multiply both sides of an equation by anything we want. So we've taken care of that first order of business. Next up, we want to look at this guy. We want to multiply it by the denominator, x times x minus 2. And now this wonderful bit of cancellation is going to happen. The x's go away. So there's no more denominator there. So you're just going to be left with 2 times x minus 2. Lastly, on the right-hand side there, let's get rid of this. On the right-hand side there, it's almost like we took this denominator and just multiplied it over to the other side. So maybe you can see that the denominator is now just completely gotten rid of. It's like if you were solving this equation, x over 3 equals 7, and you just say, oh, well, all I'm going to do is take this 3 denominator and just multiply it over to the other side. That's a good way to think about it. So you're just left with x equals 7 times 3, or 21. And that's all we did. We took this denominator, multiplied it to the other side, but we had to multiply it to everything on the left-hand side. So let's see, I got a message. Or maybe I didn't, never mind. So basically, the reason we chose x times x minus 2, for now, let's just say that it worked. It worked, it got rid of all the denominators on the left-hand side. More specifically, though, it turns out that that is going to be the least common denominator. The least common denominator. So we'll talk about least common denominator in my next example problem that I have here. But yeah, basically that's what's going on. X times x minus 2 is the least common denominator. And the x over 3, that was just a little example business we did on the side. It was not part necessarily of this problem, but it just drove our justification for multiplying both sides by this denominator.
Thank you.
So now we got to solve this guy, but notice all the denominators are gone. They're all gone. So what we need to do now is we need to simplify it. We're going to actually need to distribute this x. We're going to need to distribute this 2. And let's see what comes out of that. So over here, I distribute this x. I'm going to have that. Over here, I distribute this 2. I'm going to have that. Distribute the 2. And then I'm going to have equals negative 4 over here. Now let's see, I want to start combining like terms. Let's see, what are some like terms? Would you guys say that these are like terms here? Yeah, we got a single x plus 2x. So when we combine like terms, that's going to become 3x right here. The 7x squared is just by itself in the world. It's forever alone. Now, what I have left is I have this minus 4. I have minus 4 on the right-hand side as well. So actually something wonderful happens. If I try to move this 4 over, you could say I'm moving this one over here to the left so that everything's on the same side. Well, they're just going to cancel out. Minus 4 plus 4. And so there's nothing left on the right-hand side, and the minus 4 on the left-hand side goes away. And so all I'm left with now is this equation here that I need to solve. And again, the nice thing about this one is that there is no plus c, there's no constant over here that I need to worry about. So this means I can just factor out an x. I can factor out x. And now I need to give myself a little more space. Here we go. So I'm left with this equation down here, x times 7x plus 3. We take each factor, each individual factors, and set it equal to 0. So that's going to give us x equals 0, and then 7x plus 3 equals 0. We can solve it. You can get 7x equals negative 3. Divide both sides by 7. And the two solutions that you're going to get are x equals 0 and negative 3 over 7. So the very original equation we solved, its solutions are x equals 0 and negative 3/7. Wait, is there a problem with one of those solutions? What do you guys think as I inch ever closer towards the issue? It's this. Remember, all the way back at the get-go, before we even jumped in and started doing any heavy lifting math, we said, okay, we need to figure out what is the variable not allowed to be. And it's not allowed to be 0, it's not allowed to be 2. If it was, then that means that we're going to end up dividing by 0 in the very original equation we're trying to solve in the first place. And that's a problem. So that's actually not going to be a solution, the 0. The negative 3 over 7 is going to be our only solution. So that's the answer here, negative 3/7. So sometimes you're going to have that. You get all the way down to the end, and you're trying to put forth a solution that's not actually a real solution here. And you're going to have to cross it out and just go with whatever's left. If for some reason negative 3/7 was also one of our restrictions, if it was up here, then, and we crossed out both possible solutions, then the answer to this one is that there's no solution. There's nothing that works. There's no value you can substitute in for the x that's going to solve anything for you. Okay, so that one's down, negative 3/7. Let's try one more, and let's also see what it means to be the least common denominator. What it means to be the least common denominator, and it should click a little bit more in this next problem. So let's solve one that's going to look ugly, but it turns out it's actually going to be a little bit easier to solve than the last one was. So how about 4 over, we're going to switch the variable to the letter d, d squared plus 2d minus 8 plus 1 over, and it's a doozy, d squared plus d minus 6 equals 1 over d squared plus 7d plus 12. Now, you look at that, everyone go, ugh. Literally, you can go ahead and go, ugh.
They did.
They did, okay, good. Yeah, that's definitely one that's like a, ooh. Okay, so let's slow down for a moment. Let's take a moment to breathe. This one's not going to be as bad as it looks. The major thing we want to keep in mind here is that factoring is going to take place. We want to factor things. We recall that, well, we also have to take into account any restrictions. We have to throw out any values of the variable that would cause us to divide by 0. The beautiful part of that then is that if we just factor each of these denominators, factor, if we factor them, it's going to be a lot easier to set each of them equal to 0 to decide what should and should not be a restriction. So let's see if we can't just factor some of these. The nice thing is each of them just has a 1 in front of this squared term, so factoring is going to be pretty straightforward. Remember, so in this first one, we are looking for two numbers. Where's my text box? We want two numbers that multiply to, in this case, -8, but add to 2, the coefficient of the middle term. Can y'all think of two numbers that multiply to -8 but add to +2? Let's see, what do we got? What's that? 4 and 2 is on it, but 1 has to be negative. Very good. Yeah, +4 and -2. Multiply them, you get -8. Add them, you get +2. So that is actually going to completely tell us how this factors. So this denominator is going to factor as, well, let's just write it in there. We will write it as d plus 4, d minus 2. Don't believe me? FOIL that boy. D squared minus 2d plus 4d. Those middle terms condense into just plus 2d. And then 4 times -2 is -8. So yeah, it turns out that's a perfectly good factoring. Next up, how would this factor? How would this factor? Let's say we want two numbers that multiply to -6 but add to +1. And yeah, 3 and -2, ding, 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 those are going to do. So now let's just bring those in to bear here. +3, -2, you said. So it's going to be d plus 3 times d minus 2. And yeah, we can substitute it in now because factoring is just rewriting the original expression in a different way. Finally, d squared plus 7d plus 12. You should see two numbers that multiply to 12 but add to 7 would be 3 and 4. It looks like it'll work. So it's going to be d plus 3, d plus 4. And believe it or not, you might think, oh, we have to do all this work just to get the restrictions, and then we still got to solve the thing after that. But by doing the factoring now, we are actually going to save ourselves a lot of headaches later on. So let's see, we technically need to set each of these denominators equal to 0. Let's see if it'll just copy and paste. It will not. Okay. We need to just set each of these denominators equal to 0. So I need to set this first one, d plus 4, d minus 2 equal to 0. So then I would just take each individual factor, set it equal to 0, and you'll see you'll get -4, and this other one would be +2 if I just put them on the other side. So I know that some of my restrictions include that d cannot be -4, and it can't be 2. So those are my first two restrictions. But notice this cute little pattern that's going on here. Here, the d minus 2 factor is repeated. So normally I would have to set each of these factors equal to 0, and I have to say, okay, d, let's just do it. D plus 3 times d minus 2, that would mean that d equals -3 and d equals +2. But we've already taken care of that +2. It just so happens it's a similar factor to the one before. So we don't need to write it again. We already have taken care of it. So the only new piece of information that adds is that d cannot be -3. So d can't be -4, +2, and it sure can't be -3. And wait a minute, look over here at this last one. We have to set every denominator equal to 0, technically speaking. But look, the d plus 3 would just give us a d value of -3, which has already been taken care of. d plus 4 would give us a d value of -4, but it's already been taken care of. So yeah, technically we should do it, but if you just see the pattern there, we don't have to worry about it. That one has already been put into the books, if you will. So these are going to be our restrictions. If we work this problem out and we get any solutions that are one of these three numbers, we actually have to throw that solution out. We say, no, you're bad. So we've taken care of our restrictions. Oh, but here's the beautiful thing. By already having it factored, we have already done it. It's almost ready to it's ready to just pop, I promise you. Here's what's going to happen now. We want to get rid of denominators because that doesn't look like something I can solve the way it's written. I'd like it if there was no denominators, there were no fractions or rational expressions to worry about. And I agree, that would just be thebomb.com if we could have that. Here's how we're going to get it. What we're going to find is we're going to find the least common denominator. And once we find the least common denominator, we're going to multiply everything on both sides by that least common denominator. Here's how it's going to work. The least common denominator, since we want to multiply both sides by it, we want these denominators to all cancel out. We want them all to cancel out. And each of these individual fractions is going to get hit by that least common denominator. This one's going to get hit by the whole least common denominator. This fraction will get hit by the whole least common denominator. And so will this fraction. So in order to get the cancellation we want, the least common denominator needs to have a d plus 4 and a d minus 2 in it as factors so that these will cross out. So here's what I can tell you. The least common denominator at least needs a d plus 4 and a d minus 2. And they're being multiplied together technically. And if we get that, boy, that's going to knock these out here. For the next fraction gets hit by the same least common denominator. This one now, you need to have a d plus 3 so that it crosses out with this one. You also need a d minus 2, but wait a minute, we already compensated, we already took into account the d minus 2 here. Ooh, so the only piece of the puzzle we need to add to the LCD is a d plus 3. Finally, this last fraction will get multiplied by the least common denominator, but it's beautiful because it needs a d plus 3, which has already been taken care of. It needs a d plus 4, which has already been taken care of. So we don't need to add anything new, special, or fresh into the least common denominator. And so here's what I'm going to do. And this is all based on the mathematical idea that I can multiply both sides of an equation by really any number I want. If I wanted to just come in and multiply both sides by 17, I could do that. Why would I want to? No, I don't want to just multiply by any old thing, but I could if I wanted to. But now I am going to invoke that idea so that I can multiply by something that's smart, something that's going to help me actually solve this bad boy. So here's what I'm going to do. I'm going to multiply everything on both sides by that LCD, and we're going to get some cancellation. The LCD is all of all three of these factors. So, you know what? I'm just going to use text because it's easier. I'm going to multiply both sides by that entire expression. I'm going to multiply, so when I multiply both sides, I got to do it to basically this fraction here, also to this fraction here. Oh, okay. That's not what I wanted you to do, goober. There we go. And so now this one also gets hit with that least common denominator. And so does the last fraction here. Everything gets hit by it. Bada bing, bada boom. Here we go. And I don't know why. Zoom does not like to just use a copy and paste. I've tried it. So everything got hit by that least common denominator. Now we got to do the fun part, the part that was the whole reason we even found the LCD. It's because we can cancel out factors. Oh, that D plus 4, that D plus 4, bada bing, bada boom, they're gone. That D minus 2, that D minus 2, gone. Now we're still left with this D plus 3, but there's nothing we could do about that because it was necessary for these. I also can't just multiply this one by only the two factors that I needed for this one, and then by this next fraction, oh, well then I'll just throw out the D plus 4 factor and just multiply by these two. No, I need to multiply each and everything by the exact same thing. It has to line up, or I've broken some math rules that say, that talk about what you can multiply both sides of an equation by. So this cancellation occurs. That leaves us with the D plus 4, but there's nothing you can do about that. Finally, in the last fraction, this cancellation occurs, leaving you with the D minus 2. And so now, oh my brothers and sisters, now things are about to get a lot easier. All the denominators are gone. All their factors have been canceled out in some way. What I'm left with is a much simpler equation. It's not even quadratic anymore. Hey, isn't that nice? Ain't that special? Yeah, I would just need to distribute in each case. This first one, the 4 distributes. I'm going to have 4D plus 12. The next one, the 1 distributes. I'm just going to have D plus 4. The last one, another 1 distributes and just gives you D minus 2. Now let's combine like terms. On the left-hand side, 4D plus D. Oh, that's going to become 5D. 12 plus 4. Oh, that's going to be 16. And then we have a couple options for what we can do here. Let's subtract this D over. So I'm going to have to clear this space up top here. I don't want things to overlap too much. You go away. Okay, so there we go. So let's see, we're going to get 4D plus 16 equals negative 2. So what's left? And then since we want D by itself, we're going to move this 16 over. 4D equals negative 18. Now we got to divide both sides by 4. Finally, we're almost done. We're going to be left with negative 18 over 4 as our answer, which reduces to negative 9 halves. All right, so let's see the forest from the trees. We only got one potential solution. That's fine. We didn't do anything wrong. Is this potential solution, is this going to have any issues with those restrictions up there? What do y'all think? No? Yeah, I agree. No, it is not. It's negative 9 over 2, which is not negative 4. It's not positive 2, and it's not negative 3. So we don't have to worry about that. The restrictions turned out to not have any issues with us. Second of all, this is the solution. What that means is negative 9 halves is the only number that we could have plugged in all the way into the original equation and gotten a true statement out of it. That's what we're doing when we are hunting for a solution. We're hunting for a solution. And we're done. So let's pause for a moment. Let's take a nice breath. Everyone breathe in. Breathe out. Hopefully this doesn't sound terrible on my microphone. All right. Let's review real quick what we just did. We had a rational equation. That means there were denominators, there were fractions involved. In dealing with fractions and things of that ilk, there's a chance you could accidentally divide by 0. So we had to put restrictions on the variable. Once we put restrictions on the variable, then we have to say, all right, we need to get rid of denominators. We need to find the least common denominator, and we need to then solve what's left and make sure what we get is not a restriction. How many questions will be on the exam? I believe it's something like 15 to 20 at the moment. But again, the exam is designed to fall under the amount of time you need. And there's actual metrics that show what the average exam time should be. And it should take, on average, well less than 65 minutes, but you do have that much time to actually take it. And again, definitely you want to share your scratch work with me so I can go give you some points back. Okay, so let's get rid of all that. So the next thing we need to talk about, so this section 1.6 here, we're just solving kind of exotic types of equations. Let's talk about radicals. Radicals. Now a radical is going to look like this. It just kind of looks like the square root sign. In fact, it's just sometimes also called the root sign. Except we can throw an n on there. N, I'll put it in green. And we can say we're taking the nth root or the nth radical. So what a lot of people don't know is that if you just have that, and there's no n here on the perch, what that secretly means is there's actually a 2 there. You're actually taking the square root whenever you use that, which is the second root. However, that's an implied 2 if it's not written there. But after that, you can have a third root, a fourth root, a fifth root, and so on. You can have take roots to your heart's content. Well, here's what happens when you're taking a root. If you wanted to rewrite that as a simple exponent, a square root is actually a 1/2 power. It's a fractional power. So whatever's on the inside of your radical, if you're taking a square root, you're raising that thing to the 1/2 power. And the pattern kind of goes from there. If you're taking a cubed root, you're talking about a 1/3 power. The fourth root, a 1/4 power. And so on and so forth. And this is simply by definition. This is just a definition of what those different kinds of radicals mean. Well, what that's going to do for us is that's going to give us a situation where we might have to do some solving of radical equations. We might have equations where, oh, suddenly we're throwing x there inside the radical, and we're just going to have to see what comes out of that. However, there's going to be a way to solve these. There's going to be a useful way that we're going to solve them. Namely, if you have 1/2 power, in order to get rid of it, you need to square both sides of your equation by something. Or over here, if you have a 1/3 power, you're going to need to cube both sides of your equation. You need to cube it so that the 1/3 and the 3 cancel out, and you're just left with x by itself. That's going to be kind of our, it's a little bit of a slapshod solution to some of these things that we're about to look at solving. But let's look at some examples of this. Let's look at some examples of this. Let's say we have some equation. Our goal is to solve it. Solve. Square root of 5x plus 76 minus 8 equals 2x minus 1. Let's say our goal is to solve that. Well, there's no clear-cut way to do that from the get-go, and we only just barely discussed what a radical even is, how you can rewrite it. So here's what we're going to do. Let's take the radical expression here, this guy, and let's isolate it. Let's get it completely by itself. We can't quite isolate the variable x just yet because this x over here is not in a radical. This one is in a radical. So they're not quite on the same playing field just yet. So let's do this. We're going to add the 8 over so we can get the radical by itself. Now on the right, that's going to become 2x negative 1 plus 8 will become plus 7. Now, what we're going to do is we need to deal with the radical now. We need it to be gone. We need it out of the picture. So what I'm going to do is I'm going to rewrite this. This whole left side is inside a radical. And we just argued that if there's no number here, you're taking a square root. It's implied you're taking the second root. So the way I can rewrite this, I'm going to put it in parentheses. I'm going to draw better parentheses than that. I'm going to rewrite it so that it's written to the 1/2 power. I didn't do any special math magic here. All I did was rewrite what we already had. Now let's move it all down a little bit. You too. And here's what I'm going to have to do. I'm going to have to raise both sides to the second power. I'm going to have to square both sides because this 1/2, I want it gone. You're trying to get rid of this radical because it's just messing up the program. The way I'm going to get rid of it is to take the reciprocal of 1/2, which is 2, and raise both sides by it. So I'm going to take this whole left-hand side and I'm going to square it. But everyone out there in the Zoomosphere, can you just do something to one side of the equation and not the other? No, you cannot. You can't just decide, oh, I'm going to manipulate the left-hand side only. That's not how it works. You're going to have to square both sides. You're going to have to square both sides. And so here's what happens. This 1/2 and this squared cancel out. If you don't believe me, you might remember the exponent law that says I would just have multiplied those two exponents, and that would just give you a 1 exponent, which is not doing anything. But that's kind of what we're doing here. We're getting rid of the radical by raising both sides to the reciprocal power. Now on this right-hand side, boy, it would be nice if squaring it just meant, oh, I just square the first term and then I just square the next term. Unfortunately, that's not how it works. Do we have to raise both sides to the 1/2 power first, or can we just square both sides? Great question. all we're doing when we're initially doing, we actually aren't raising the left-hand side to the 1/2 power. We're just realizing that it already was written to the 1/2 power, just in a different way. By using this radical here, that's secretly saying that, oh, well, the left-hand side here, this part, is already being raised to a 1/2 power. So we didn't technically raise it to a 1/2 power, we just rewrote it so that we could see the 1/2 power that was in hiding. What we did do though was we did raise both sides to the 2nd power. We did square both sides so we could get rid of this 1/2 power here. Exactly, we can square it while it's still under the radical, because what we're doing is by squaring both sides, we're getting rid of the radical completely. We're getting rid of that 1/2 power, and now it's just 5x plus 76 living its best life with no radical anymore. But the fallout of that is that the right-hand side, when we square it out, well, there's just no other way to say it. When you square something, you're multiplying it to itself. So the way we're going to deal with the squaring now, we're going to have to multiply it to itself. Which means we're going to have to FOIL. But the good news is that there's no more radicals. No more radicals. Everything's on the same playing field now. We're going to FOIL out this guy. The 2x, the 7, da-da-da. We're going to FOIL it out. The left-hand side hasn't changed. Oops. The right-hand side, 2x times 2x. 2 times 2 is 4. Then to deal with the x's, x times x is x squared. Then completing the FOIL, 2x times 7. 7 times 2x in the middle. Finally, 7 times 7. It's going to look a bit like that. So now we need some more space. Let me create some space for us. You go. Let's bring this all up here to the top. So we're doing it piece by piece. Now on the right-hand side, let's combine our like terms and simplify. These 14x's in the middle, well, they're going to simplify into 28x. That's not looking good. There we go. The left-hand side doesn't change or anything. And now that we have something that looks a little bit like this, we're down to a quadratic. We have no more radicals in the equation. We need to basically get everything on the same side of the equation. So I'm just going to move this left-hand side over. Move everything over here. I need to move this 76 over. And now we have a little bit of math we need to do. Of course, the 4x squared is fine as it is. Four x squared is good to go. 28x minus 5x is going to be 23x. 49 minus 76, well, I'm taking a larger number away from a smaller number, so I know it's going to end up being negative. Now that I know it's negative, I kind of flip it on its head, and I do 76 minus 49. So I'll need to use some borrowing. Looks like it's going to be 27. And it'll actually be negative 27. So we've got some nice Christmas colors here on the whiteboard. So we're going to have to clear some space again. And so now we're left with this thing, and since we moved everything over from the left-hand side, there's a big fat stinking 0 over there. So now we're left with this. We've done a lot of mathematical heavy hitting already so far just to solve this problem. So if you're kind of sensing a theme forming out of this, it's that, frankly, a lot of the numbers we're going to deal with and a lot of the processes we do in college algebra are just nasty. Some of these problems just keep going and going and going, like the Energizer Bunny. How can we deal with that? What's our way around it? Unfortunately, college algebra is just a grind. I mean, I'm already sitting here. We haven't even fully finished this problem. It's been like 15 minutes. And I mean, with me having to explain everything, of course, it takes a while to do some of these problems. So that's the unfortunate truth behind college algebra. I wish I could say, oh, it's going to be peachy and roses, but you kind of have to come in. You got to be quick with the numbers. You got to be moving stuff around. Um, but that's not to say when you're working on your homework, you do have a little bit more time. Obviously, you're at home. So I would say take your time, make it a grind. If you run into a problem that's giving you issues, shoot me an email, shoot me a message. I usually get back on my messages in less than 24 hours, depending on when you message me, sometimes way less. Right now, our schedule has it where basically every Thursday night you're going to have a round of homeworks due. But you'll notice all the homework assignments are open for at least a week. So if you're waiting until Thursday night to do the homework, you're probably not going to be able to get it all done. It's designed for you to take about a week to do. But I also design it so that you kind of have to master your own schedule to make sure that you can do it in a timely manner. So I would attempt a homework pretty much as soon as you can. I would get out there, try out some of the problems, and if you have issues, you can come to me, you can let me know. Unfortunately, the class time we meet, I mean, we're bare bones. We got to rock and roll during class time. But there is time if you message me, reach out to me individually, there's definitely time for that and to get extra help. And I'm always super willing to help. So that's kind of the admission I have to make to you guys is that, boy, we gotta rock and roll when we get in here, and there's just no two ways around it. So back to it. That was a nice little break. We can all take a nice little breath here. We have to now solve this one. Now, technically, there is a way to factor it, and the way we can factor it is actually not quite as bad as it looks. But there's another possibility. We could use quadratic formula. So, whoever messaged me first in the chat box, do you want quadratic formula or do you want factoring? First person to give me an answer, that's the way we'll go. And oh, we got one already. You guys are quick. Quadratic formula, that works for me, Gracie. Thank you. Quadratic formula. Let's remember our quadratic formula. I'll recite it like a Gregorian chant. No, I won't. That's a joke because I cannot sing. Now, the truth is, this one is really, we could factor it, and factoring it would kind of be our way to where we don't necessarily have to get in there and use a calculator. We may not have to here, just depends on how quick you are with the numbers. Some of the problems, though, if you choose the quadratic formula route, you may need to use a calculator. On exams, though, they are designed for you to not need a calculator. They're designed. I look at them with my eye and make sure the numbers are a little bit more simple. But when we're talking about it in theory or in class, I'm okay if we use a calculator very lightly, because you notice a calculator, it wasn't going to ever solve the whole equation for us. It's just for some light intermediate calculations. Okay, so quadratic formula, A is 4, B is 23, C is negative 27. So according to the quadratic formula, negative B, negative 23, plus or minus the square root. Now we have to do the discriminant. 23 squared, I might want a calculator for that. Minus 4 times negative 27. Had we factored it to solve it, we probably wouldn't have needed a calculator. But it's always good to get exposure to the quadratic formula. I say we deal with the discriminant right now. I say we deal with the thing inside the square root at this juncture. I think that would be most beneficial. Let's bring it down here. And yes, we'll just go ahead and pop things into a calculator for the moment. 23 squared is going to be 529. Now notice I've got negative 4 times negative 27. That's going to turn into addition altogether. Let me write a better plus sign than that. That's going to turn into addition altogether, and that's going to become 432. And altogether, we're going to get 961 for the discriminant. So it's going to be a 961 in here, is what that simplifies to. Now, again, you may not realize it, but 961 is a perfect square. It doesn't look like it. 961 almost looks like a prime number, but it's actually not. What this is now going to simplify to.
No.
What's up?
I'm saying square.
Oh, yeah, square root, square. Yeah, I think it's just because in a calculator you just see SQRT. So yeah, it's a tease. Square root of 961, squirt of 961 is 31. Now we're going to deal with the plus or minus, but since everything looks like a whole number at the moment, let's deal with it this way. Negative 23 plus 31 is glorious, glorious 8. And we have 8 on bottom. Whew, that works out real nice and clean. So one of the solutions is the number 1. Negative 23 minus 31, well, you know it'll turn out to be negative. And then you know that 31 plus 23, maybe you can do it. That's going to be 54. So it's going to be negative 54 over 8. And now the only thing you can maybe do is you can simplify that into negative 27 over 4. Let me give myself a little more space. You can simplify that fraction just a tad. Negative 27 over 4. So these are going to be 2 potential solutions that are going to work. And so you say, yes, Mr. Gunther, we're done. Thank goodness it's over. Oh, huge relief. Almost. There's always a but in college algebra. It looks like it's done, but there's one last thing we need to remember, or one last thing we need to worry about. What happened was when we squared both sides, remember how we got rid of that radical way back when, like literally 20 minutes ago? We squared both sides of the equation. When we did that, we introduced some gremlins. We allowed some gremlins into the problem. What do I mean by gremlins? We allowed the possibility that a negative number could work because let me put it another way. We introduced the possibility of negative numbers getting in there when they shouldn't be. And it's because squaring both sides of an equation is actually not super mathematically sound. The way we deal with that problem is we need to check our solutions. We must check. We have to check that our solutions work. We have to check that our solutions work. How do we check them? We take both of our proposed solutions and we plug them in all the way back over here into the original equation. Now that's going to create a little bit of a pain, but it must be done. It must be done. So let's give ourselves some room here. You go, you go, you go. What we'll do is we need to check 1, and we need to come all the way over here to our original equation and plug it in for x. And just make sure that everything we're doing is going to be mathematically sound. So 5 times 1 plus 76 minus 8 equals 2 times 1 minus 1. And what I'm really doing is I'm plugging it in and I'm asking the question, is this over here on the left equal to this over here on the right? I'm asking the question. We'll do some quick math here. That's going to become 81 minus 8 equals 2 times 1 is 2 minus 1. That becomes that. Square root of 81 is 9. So does 9 minus 8 equal 1? Everyone says yes. So that's going to check off. That's going to check off. And that means 1 is indeed going to be a solution. 1 is good to go. Now, negative 27 over 4 is going to be the more interesting one because it involves fractions. We're running a little short on time. So we'll speed through it, speed racer it. And what we're going to see is that things are going to get nasty pretty quickly. We need to check if this is true. We need to make sure it's going to work. What we're really ultimately checking is we're making sure that we're taking the square root of something and that we're not going to get a negative number out of it. But remember, we're subtracting the 8 as well. So let's actually move the 8 over. And so you don't have to go all the way with it. You don't necessarily have to completely solve it. We can use a little logic here. I'm going to add that 8 over. And now let's just eyeball it. Yes, 5 times negative 27 over 4 is going to be nasty. It's going to end up being a negative number. But I think the 76 is going to take care of it to where I'm still going to be left with a positive number on the inside here. This is still going to be positive. So I'm only taking the square root of positive numbers, which is good. That's sound. Taking the square root of negative numbers involves I, and we're actually not wanting I to come into the mix at this particular moment. Over here as well, if we deal with this though, on the right-hand side, look what's going to happen. You do 2 times negative 27 over 4. You could rewrite it like that, and I know we're doing a little quick. Negative 27 over 2 is about negative 13.5. You add 7 to that, it's not going to make it positive again. So we're trying to take the square root of something that's positive over here, and we're trying to say it's equal to a negative number. That's not going to happen. Our square roots need to only spit out the positive form of that. That's a problem. What that's going to mean for us? No, that's not a solution. So only an x value of 1 is a solution. All right, let's take a big breath because that problem was nasty. It wasn't fun. And that is just the unfortunate truth of college algebra. I wish it was different, but it's not. I will post a recording of this lecture here. It'll be on the YouTube channel in a couple hours. I implore you, work on your homework, send me questions you have. Monday, we still have material to get through, but I will try Monday to allay any fears you have about the first exam. I'll just come out and say it. The first exam is not meant to make you cry. It's meant to be very straightforward. And especially if you're taking good scratch work, I will give you back as many points as I humanly possibly can, because I know this material is a little tough here in chapter 1.
First exam, make sure and upload your work.
Yep, exactly. I'll show you exactly where to do that. I will let you know on Tuesday exactly where that's going to look like. All right, we're out of time. You guys have a great day. Thank you so much. And we will see you. Have a great weekend.